Automated Testing Embedded Code with Kevin Kirkus.
The Azure DevOps Podcast is a show for developers and DevOps professionals shipping software using Microsoft technologies. Each show brings you hard-hitting interviews with industry experts, innovating better methods, and sharing success stories. Listen on to learn how to increase quality, ship quickly, and operate well. And now your host, Jeffrey Palermo.
Welcome to the show. I'm Jeffrey Palermo, your host for helping you and your teams move fast, deliver quality, and to run your software with confidence in Azure, all while using everything the .NET ecosystem has to offer. The podcast is sponsored by ClearMeasure, a software architecture company empowering .NET teams to be self-sufficient and delivering world-class results. ClearMeasure is hiring architects and .NET engineers who'd like a path to become an architect. So go to clearmeasure.com/careers for that. The guest today on the show is Kevin Kirkus. He is a principal engineer at Intel. He's been there since 1999, designing, building, and testing Intel processors, both the chip and the code that runs the chips. And he's a post-silicon validation architect lead for multiple Intel Xeon generations, and more recently transitioned to global post-silicon automation lead for server, client, and device products at Intel Corporation. He has served in various past areas of validation like PCIe, socket-interconnect, platform configurations, boot flows, views, before transitioning to more technical leadership roles in validation architecture and strategy. As a technical leader in silicon validation automation, his roles and responsibilities have extended to global standardization and alignment of tools, flows, and methodologies across Intel global product segments like server, client, device, including mentoring environment domain leads, aligning global sites, and strengthening local product sites to excel in automation investments. His technical and leadership experience for validating advanced complex technology has been integral to the success of Intel product teams and their competitive products. And he is super passionate about developing people and future leaders, building on their strengths and influence and impact. Kevin, welcome to the show. How are you, sir?
Good. Thank you, Jeffrey. Doing well.
Awesome. I'm really excited to have you on the show. We have so many guests and topics about high-level code and testing and DevOps processes and what it means to make sure everything is working properly. But you're making sure that Intel processors are working properly. That blows my mind because I've never worked in that space. But before we kind of dig into that, and you've been at Intel since 99, 22, 23 years. Give us a sense of when you made the mental transition, you know what, this is what I'm going to do. This is cool. I'm going to make a career of this. And what are the high points that kind of have led up to what you're doing today?
Yeah, so I first started out in pre-silicon world where you actually have to simulate, and every clock for clock cycle has to be executed, which takes 24 hours to even run a test. And then you realize you're having to farm this out to a lot of simulators to get your results. And that had its moments of definitely teaching you low microarchitectural stuff. But that led me to my particular site that I was working at had both some pre-silicon activities and some post-silicon activities. So I started dabbling in the post-silicon side, and that kind of drew me in. It really helped me to see a much bigger picture of how this product, this CPU in this case, is going to be used beyond just the clock for clock and the RTL or low-level register transition logic. So that kind of helped me see, well, great, this is actually something I enjoy doing on the post-silicon side because I got to do some test planning, some content development, some debug skill sets to kind of find bugs in this post-silicon world. So to produce a high quality product to give it to the customer eventually. And you kind of develop this, a little bit of an edge to where you don't want any bug to escape that was in your particular domain area. Mm-hmm. So I started out in PCI Express, the first generation when they ever productized it in the industry. I got to work on the first one as a prototype before it was going out. And that kind of helped me understand what it takes to actually make this work from the ground up. looking at the physical layer, the link layer, the protocol layer, and you start living in these world of layers that all have to build up to operating system validation. And then you're really getting to see all the inner workings as well as the broad picture of what it takes to be a logic validation engineer, which is what our role is called as functional validation. So from there, I actually we started to shift some of the ingredients in our CPUs. You'll see a lot of logic blocks in the hardware start to move around, where you may have a core next to memory, or the memory may be in a separate die. You may have I/O devices separate from the rest of the system. You have a lot of these different interconnects. So one of the first generation interconnects between sockets for Intel, I got to be the owner and validate that post silicon. So that really kind of led me to a larger scope of multiple domain type expertise. So I started working with the power management team and the PCI Express team or the memory controller team. All these different domains, we call them, had to come together to work on the same CPU to validate. And they needed to have leadership to kind of look across that. What is the shared systems they're going to be using? How many platform configuration varieties do they need to represent the customer's potential space? How do we get everyone to kind of coordinate together under a validation discipline and a validation goal of finding as many bugs as possible before we have to reach the customer? So that's kind of what shifted me a little bit to a little more broader multi-domain, multiple configuration, helping out with the first silicon power-ons, booting the system up to the operating for the system for the first time, and then bringing it all the way to the point where it comes to maturity. And I started realizing that there's a lot of need for flexible configurations, flexibility in testing, capturing as much data as possible for the debuggers to triage. And that kind of led me toward the automation space. So I started engaging mostly with what we have a special validation operating system that we use. And that's our primary, for our team, is like 80% of our validation methodology. So getting all the validation packages and the validation software and all the test integration, all working on prototype hardware, is extremely difficult because not all these pieces are ready as we would like them to be. They're all in the prototype stages, and trying to incrementally grow that product to a mature point, as well as all the ingredients associated with it, requires a lot of good cross-domain teamwork and other things. That's what kind of led me to looking at, I want to be, an automation person. I want to focus on functional validation execution. And I like post-silicon because it lets me see the big picture from when it becomes a sand to silicon, and then it becomes a product to the customer, where I'm involved in the full starting point of that to the end. So it's been a fun roller coaster.
And just to ground the listener in kind of what we're talking about, a few episodes ago, we had an episode on embedded software. We talked about embedded Linux on Wilderness Labs, IoT systems on a chip, and kind of the bubblegum stick sized computers that are out in the field doing stuff. And so that's where we can't just test the code that we wrote. We have to test it running on a specific chip, talking to a specific set of electronics, circuitry, whatever that happens to be. But yours is a whole nother world. Can you give us an overview of just what that landscape is? You work on the Xeon processor line, but of course Intel does all kinds of different chipsets. And talk about what type of code runs in those, and then we'll go into the testing methods.
Sure. Yeah. So when you think of a core today or CPU, it's made up of it's multiple dies that may fit inside of a package. Each of those dies have their own responsibility, and they're often interconnected to make these what they call IPs or subsystems, or what ultimately becomes your system on the chip. And you'll have what sometimes we call the North Bridge or the South Bridge. And this depends on whether you're dealing with the core and the memory controllers and the cache coherency engines, or PCI Express, or whether you're dealing with more of the South Bridge, which, for servers is not not as much as what you see in client, but you'll still plug in a mouse and a keyboard, but you're not caring about all the US Type-C and stuff like that on the Xeon. But what we try to do is when we're looking at this big picture of how does a flow of transactions actually work in the system, we have to decompose it. If I'm going to be starting at the top level of running a user app, ultimately it decomposes to some library or driver, or ultimately to the kernel to maybe talk to some system memory, a malloc or something. So we have to figure out, well, what does that actually result in the hardware? Now, my particular Xeon, proximity of the things that we test, we have this concept of a core, which would be all the many cores that you have in the system. We have a concept of a socket where I may have one socket or a two socket. When you get your laptop or PC, that's usually a single socket with, let's say, 4 to 6 cores or something like that. Where in the Xeon class, you're tripling that. You're getting to a very, very large number of cores, but you also have more than one socket. We have one socket, two socket, even 4 socket, in the very high end at HPC, you could even get 8 socket systems. And they're all interconnected to create these hypercubes and other things to really maximize your performance and throughput and large memory scope. But that core that's inside there is extremely sophisticated. It has its own dedicated team just to focus on the core, one core or all of them. And then I work on the area where it's more of the system on a chip model, where I'm looking at what we call the uncore. And the uncore is everything, not the core.
Gotcha.
And if you think about the core executing instructions, which most of the time when you're running software, that's almost 95% or more of what you're doing is literally just sitting inside the core and running. And when it goes outside the core, it's when you're going into the caching systems, right? You're trying to make sure that 2 threads that are talking to each other with the same memory do not have some type of performance issue or logic issue where you have some bit flip and you didn't expect it, what we call data miscompares. So we're focused on the flow of the thread talking to memory, or the flow of an I/O device like a PCI Express card or graphics card talking to memory or talking to each other, or the cores talking to the I/O. So we're looking at all the system flows in the uncore to make sure that we don't have any issues with cache coherency, memory coherency, bottlenecks in the system that produce bugs. And that's our job, is to find those bugs in that uncore, to ensure that we don't have any escapes to the customers when they go to run any workload. So one big difference about a functional validation engineer is we operate heavily by spec. So the architects will define, here's the feature set. The designers will go implement it. And then we're actually supposed to validate that feature, but we're trying to validate that feature in every corner of validation space that we can, because we don't always know the way the customer may use it. And we try to learn from the customer, what are the use cases, what are the requirements that they may have on how they might exercise it. But it's also oftentimes a mystery to some degree, because you can think of the competitive nature of their world. They don't want to share all their individual feature usages to make them less competitive with another company. So we only have a little bit of visibility as to how they might exercise it. There's been cases where we may find an issue 5 years after we've productized, just because the technology and the software and the compilers have morphed over time, revealing vulnerabilities to our hardware. So we're trying to cover, with a single OS or a couple of OSs, maybe a representative sample of 10 different operating systems and 10 different kernels that the customer may eventually use. And so we're trying to make this as solid as we can from a spec perspective, while still keeping in mind our validation efficiency relative to the use cases of the customer.
Okay. And so these chips, when you say post silicone, that means the code is embedded, the silicone's made, and you have something where if there's a bug, it gets thrown away and we try again. Am I on the right track?
Yeah, it's a little bit of a trial and error, but each fix has its own consequences.
Right.
So in the hardware world, if we have a hardware fix, we're looking at weeks upon weeks or months to actually fix a new stepping, because the silicon turnaround is slow. It requires a respin of the manufacturing. If you're a base layer or a meta layer stepping, they go through the pipe much slower. Whereas if you have firmware layers on top of it, because we have about many microcontrollers that are inside of this processor that have firmware of their own, and we can patch those firmware. They come with a ROM, but we can actually replace some of the instructions in the RAM. And it gives us a chance to work around some of those hardware issues. But at some point, there are cases where you have no choice but to make a hardware change. If you can fix it in firmware, it's great, but you may pay a penalty of a power or a performance hit as a result of that choice. And some of it can even be worked out through BIOS, which is the next layer up, to where you may be able to set a register to turn on a particular debug feature or a workaround inside the silicon. You're now playing around with these layers, whether it's the hardware that has to be fixed, or a firmware that can be patched, or a BIOS that can actually adjust the feature or defeature it in case it doesn't work. Those are the major stacks of control we have, but they all have different, I would call them penalties as to the turnaround time for a fix.
Yeah. And so this code, there's programmers who are writing this code. Is all of this assembly language, or what is the mix of actual code types that are a part of this?
Yeah, so some of the microcontrollers, they're trying to get away from the assembly because it's just too complicated to read.
Yeah.
You can have too much user error. So you'll see some of them dabble in areas of programming it in C or some other abstraction layers. It's a different programming when you're working on microcontrollers because it could be more of a parallel processing type microcontroller where it's doing loops with inner and outer loops and things like that. Where if you're getting up into the kernel space, that's more serialized and it's going to be executed on a single core or spread across multiple cores for efficiency. So that embedded firmware is lower level, but it is a little bit abstract just to avoid user problems with doing it. But once you go up the stack, you'll start seeing very much the same, operating system code up to user apps, which can be all kinds of languages. That's just the nature of the choice of the individuals.
And you mentioned turning off a feature, defeaturing something kind of in the testing process. So it sounds like you guys have been using the concept of feature flags for a long time, which has been popularized in user applications about just having some type of configuration to enable or disable or hide a feature. How much of those do you have? Is it kind of pervasive? Is that just normal for every feature, or is it just for experimental ones?
Yeah, it's a tough balance. There is a concept called fuses, which is what we call SKUs or stock keeping units. So when we produce a product, the product that goes to one company over another may differ in the fuse, and this actually can turn on and off features. Because like I mentioned with the different sockets, if you have a 2-socket part, you don't want to have that being used in a 4-socket platform because there may not be the right compatibility. So you can use these fuses to kind of differentiate. That fuse is at some granularity, a feature granularity. Like for instance, it's 2-socket capable. Therefore, I can downgrade it to a 1-socket, but it may not have features like a high-end desktop has, certain power management controls, overclocking, things like that. Where if it's on an 8-socket system, it may have advanced RAS features, or what we call reliability, availability, serviceability, or manageability. These are the features that give you really the great controls of what happens if I'm running processor and out of the blue I have a correctable error or I have a fatal poisoning error. Can I survive and keep running? These technologies usually have an architectural feature associated with it. Some of those features are controlled through that fusing, which is in the part. Some of that feature is controlled by a BIOS, actually turning on or off that feature at boot. And the customer can sometimes manipulate some of those unique for their competitive advantages. In our world, since we're dealing with the prototype, we have direct access to our BIOS team, our firmware team. We can actually access the low-level registers ourselves. So as long as we understand how the feature is controlled, we can actually go into the inner workings and turn it on and off. If you think about the first time we're turning on this piece of silicon, I would love to say that it just boots, but it takes a lot of work. And it's a prototype of every type, every ingredient, the platform itself, the board, the BMC, the base management controller that's on that board, the debug tools, the BIOS, the operating system to some degree, because we have a modification of it custom to each project. Each of these are actually brand new prototypes that we do all of our best we can in our silicon readiness phase to try to prepare all these to be bootable, so that when we get to what we call the first power on and we put the chip for the first time on the board, we hope it doesn't smoke. and we're trying to just make sure that it boots up. And my job starts when they have gotten to the point where it boots up and it's actually reaching the point of fetching the operating system code to where we can actually see it in the operating system. But we do a lot of defeaturing in that first power on up front. We will turn off, all the power management that we can. We will not run with virtualization enabled. We will turn it to the lowest frequency of memory. We will try to run with the fewest number of cores and fewest number of threads, like hyperthreading turned off. Because again, we're trying to stage that feature enabling and that configuration complexity over time to try to make sure we don't just stumble over ourselves, because we have so many variables and moving parts. If we're not careful, we'll just end up crashing on everything we tried to test if you go too fast. But you don't want to go too slow, because then you'll never make the product deadlines. So that defeaturing or that feature control is a huge part of our staging and configuration strategy enabling to make sure that we can get to the end goal in time, as well as not really hurt ourselves in our own demise.
Yeah. But you mentioned a little bit some of the test harnesses or what you have to build to actually enable a chip to run your tests. But talk about the format of the tests themselves. Are you what language do you write the actual test cases in?
Yeah, so we have this concept for functional validation of it's a partnership between a host system that's running Windows usually, and the target system, which is running Linux for data center. For the client team, it would be more predominantly running Windows, because again, they're addressing the operating systems of their main primary customers. So you'll see client maybe 50-50 with Windows or Linux, and then server may be more dominant Linux.
And you mean the I-series processors, right?
The I-series, yes. On the Xeon side, we would talk about the E-series. Yeah.
Mm-hmm. Okay.
So the I-series is a little more mixed. So if you deal with that host and that target, the host is really there to kind of govern the operations of the target. So if you think about, I need to flash it with a brand new BIOS or a brand new, what we call an integrated firmware interface. It includes your BIOS, your BMC code, your manageability engine type controls. It has lots of different BIOS and firmware pieces that are all encapsulated inside that IFWE. But the host needs to provision the target with that, because that's not something that the target has yet. It needs to have a BIOS installed. So we can use the host to install the BIOS, and we can then boot out the machine with a different BIOS code. So that's one deployment method.
Okay.
By having these two distinctions, we now can start building, how do we want to get the whole system set up? Do I want to install a different kernel or a different Linux version, CentOS versus or Validation OS? Do I want to be able to change the IFWE on every test, or do I want to change it just before I start a suite of tests? So our automation is trying to figure out how best is it to deploy the system with the right ingredients, make sure that it's ready and checked before we run the test, because in the server world, I would phrase that our coverage is made up of about 50% configuration. That's your memory topology, your IO topology, your BIOS knobs, and the other 50% would be your test stress, running coherency testing, PCI Express stress testing, these types of things. These are the ways that we want to kind of divide the ability for a test owner to pick a particular config to give them the right coverage of a feature. So when you kind of scale that out to our testers, what they're looking for is a team like the automation team to build them the appropriate platform, give them the right configuration to give them the right cross-product coverage in the system, and then make sure that they have the ability to data collect, any failures that they have, so they can do debug offline, and to make sure that they can actually run their test in the operating system. So the testers have a choice. They could write a test that works with debug tools on the host, which might go to a very low-level register they want to manipulate, like a feature or defeature. And then they may want to run on the operating system on the target side and actually write a test that actually is using the thread and writing to memory and then checking that the memory actually didn't have a miscompare. So we have a couple of memory harassers. We have cache coherency harassers, And these are written usually in C because they need to be high performance, very good compilation to where even inside of some of these tests, we may embed some assembly code to make it super efficient on its loading and storing of instructions. Because again, as an uncore validator, I don't want the compiler or the core to get in the way. It doesn't help me if the core is executing, I would call it opcodes of no value to the uncore. I want opcodes that directly result in a transaction that leaves the core and goes to the memory controller. Because I'm a hardware validation engineer, I'm not trying to work with virtual address space. I'm trying to work with physical address space. I might want to be contiguous in my physical addresses that I'm accessing because I want to hit one memory controller over another memory controller, or I want to have a thread talk on socket 0 to socket 1's memory controller. That requires a very tight control. So these C applications are built to get the right memory on the right location and then stress the mess out of it to try to see if there's something internal with a overflow of a queue or an overflow of a buffer or a collision between two threads going to the same memory target or IO going to the memory target at the same time. That's what we're looking for. We look for data miscompares, we look for hangs, we look for correctable or uncorrectable errors being flagged as a result of testing. And that's where C works really well, is because it's very high performing. But C does not work well when I'm practicing, when I'm trying to figure out, does this product have the right registers set according to what my BIOS was intending? I could have 100 different BIOS configurations. Did the BIOS and the firmware patches program the right registers in the system? You don't want to have to write a C app just to read registers. So we use a lot of Python. Because Python being an interpreted language, we can actually write something, test it out very quickly, do a feedback loop, and kind of customize that particular Python script to do special things, whether it's kick off error injectors, dump a whole bunch of registers for future triage, because a lot of our failures, we need to gather a lot of information and do some data analytics on it. Because the enormity of information that we can collect is almost impossible for a human to go through every detail. So we're having to do a large amount of Python dumping of the system to get state, so that then we can compare one failure to another, or a person can drill in and say, I know of a particular signature that fails. Let me go straight to this particular IP or register and look there. There's a single bit flip that is very common with another single bit flip. And they're now getting into this ecosystem where they're trying to triage a large amount of system data based on a failure. And it's much easier to do that with a lot of incremental adds of software Python modules and import modules that import other modules that then let you distribute this workload. So one cool thing that we do is this Python solution we have that gives us all this low-level visibility. It's a contribution of a distributed nature. All of our domain leads, like the PCI Express, the power management, the memory, the virtualization, they all can write their own Python code that then gets consolidated into our overall set of Python project code. And when they're running their tests, they'll use their particular Python set of tests, which are built on a stack of modules that everyone gets the benefit of. But they can customize their domain-specific information, because a power management user is looking at power management across lots of IPs, but they're really focused on features related to power management, like your C states and your performance states and package C, low-level power management type things. So they're looking at something very different than like the security team who wants to look at security features. So they then customize their Python scripts for coverage purposes, for debug purposes, and for just status information to help them debug. So most of our languages are C and Python, and occasionally you'll see other people experiment with C++ or whatever new languages because they want to dabble into machine learning testing. There's just a lot of different workloads that they can approach.
Many thanks to our podcast sponsor, ClearMeasure. ClearMeasure is a software architecture company that empowers clients' development teams to be self-sufficient, moving fast, delivering quality and running their systems with confidence. Whether starting a new project or developing new technologies or techniques, ClearMeasure sets up your team to deliver world-class results. Learn more at www.clearmeasure.com. ClearMeasure, empowering software delivery.
So you've got the test harness code, you got firmware loaders, and then test case codes. You got, I'm imagining, a very significant test suite code bases. Are these stored in Git for source control, or where? And
Yes.
Okay. So
yeah, so that's a tough one because the firmware would not be in Git.
yeah,
The firmware is coming from the designers, so they have this concept of a unified patch release. So they actually have their own what we call star codes because there's lots of them, and we unify them together and we deliver that through, you lo and behold, a network share.
yeah.
And that network share is designed to allow them to just drop lots of different patches. So a lot of teams have started to experiment. Well, I don't really want to work with a network share. I really would like some type of DevOps control to where that share is then available and we can then package it or put it into some type of repo to more efficiently deploy it. The rate of change on the firmware is once a week or once every 2 weeks or something. So it gives us a chance to actually explore those types of solutions. But the hard part is I might need to deploy that firmware to both the host if I'm building an IFWE or the target if I want to deploy it to my system at runtime. So the firmware has to be handled a little bit differently. It has to be cross-platform deployment packaging. And we might need to do it at runtime. I'm actually in my operating system, and there's a concept of what we call seamless microcode. And you can actually, while in the operating system, while the thing is running all kinds of stress traffic, you theoretically, and this is what we have to test, I can patch the firmware on the fly, and it has to be able to handle this kind of code. So that firmware is kind of a special case. But when you're dealing with all the other types of Windows packaging and Linux packaging, we actually have all that in Git. And people will commit on the Linux side, and it'll automatically build the package as part of our build system. On the Windows, they're exploring using Azure to actually check in to Git or other repos that they have, and it'll automatically build some type of host package. And the challenge there is how do you ensure that you have system quality of a commit? On the target side is tough because we are trying to move extremely fast. So we allow all of our validation engineers in the Linux space on the target to commit their code, and we can immediately consume it, or we can try to run some testing before it. So we have to put a whole bunch of gatekeepers. But if you think about our gatekeepers, it's not just software. If you deployed a piece of software, you could run it on a shared server with some cloud service that's provided, and you could get feedback that software is running on healthy hardware. Where for us, when we deploy software, it may be custom to a particular product, and therefore the validation of that has to be on that product, but that product is also a prototype. So we can do our very best to do unit testing and product agnostic testing, which is some things we do. But at the end of the day, for it to really know that it's going to work on my Xeon, I need to test it on my Xeon. And unfortunately, that's what we would call an ingredient collision, because the test that's being released only works on Xeon chip A, but it was tested on A-1. So it may have worked great on the A-1. It may completely blow up on the A. And now I'm stuck trying to pick up the pieces and do a feedback loop to the validation engineer who wrote the test to say, this is not working on this product. It's great that you worked on the previous one, but that's not really relevant. You just crashed my box.
Right.
And the other part is that some features that we mentioned are cutting edge. So my Xeon A may actually have a brand new feature that has no N-1 product to test on. So now it's a playground. Now I have to almost give them dedicated machines for them to enable that software incrementally to the point it gets to mature enough to go into the general pool of machines to do more extensive testing with larger configs. So this hardware prototype balance of software releases is very different, that even if I had mature software on N-1, I'm still going to face challenges on the front lines, constantly trying to deal with the fallout when it doesn't work on my end product.
Yeah. I can just imagine how large your test lab is for all the different combinations and how many different servers, just to have enough sockets to put things in. And
Yes.
um,
Yeah.
but besides that, and how much custom you have to run your test suites, are there any commercial products that just kind of drop in really nicely, maybe to run the test suites or keep track of historical runs and be able to relate them back to bug reports? Any?
Yeah. So unfortunately, so we definitely touch on some industry solutions at times. So most of our solutions are proprietary. Our bug tracking is proprietary. Our I would say our operating system is actually built on a Debian distro, but we modify the kernel to give us validation hardware hooks. So that's a reuse of the industry. Our host is all Windows, so that's a direct reuse. So everything on the host is a Windows. We try to stay up to date for performance and other things, but in the end, it's pretty much just a deployment methodology as you would with Windows. So when we talk about things like Azure, this is a cloud service that may help us to satisfy our automation proprietary tool using Azure Cloud as a backdrop for a lot of the services. So for our automation solution is twofold. It has kind of an external cloud service capability, and it has an internal proprietary, and they bridge them together.
And you're meaning Azure pipelines, right?
So we're getting to the point where Azure pipelines will help us to build some of the packages. And we're actually trying to figure out, can Azure help us in this new territory of better use of ingredient management? So if I've got an IFWE with a BIOS coming in, could I use an Azure pipeline to not only detect that someone released it from the BIOS team, I need to modify the BIOS knobs, I need to manipulate what it's paired with on a patch case. I would love to be able to automatically create the new IFWE that is customized to my validation product, and then kick off a pipeline that executes testings with our proprietary automation. So some pieces are industry. We try to look at how the industry does this, but a lot of it is proprietary because we need so much customization. So we're kind of building hybrid systems, I would call it.
Oh, yeah, for sure.
Yeah. The Azure pipeline will kick off the proprietary automation, which kicks off the proprietary OS, which may run a commercial workload.
Right.
And that glue logic of all those layers, as you can imagine, when every one of those ingredients can be changing, the better we can do with continuous regressions to improve our continuous integration, which is like the collision of all these right before you put the test on, and then deploying it to the 100 machines or whatever. We need these gatekeeping stages to make sure we do not push something to our larger fleet of systems that has been unchecked, because the last thing we want to do is cause a failure due to our own environment problems. Because one of the challenges is that if I fail a test and hang my station, it can take as much as 3 or 4 hours of data collection just to get what the user needs to do debug offline, so I can free up the capacity of that machine to run another test. So we take a huge penalty for data collection if we have a failure. So the more we can do to, I guess, weed out those environment issues or ingredient challenges of all prototype entries, the better we can do in making sure that those volume validation machines are being used for the best credited coverage and not trying to deal with environment constantly being a problem.
Yeah. Well, as we close here today, one thing that you've also been transitioning in over the years, not just the test automation engineering, but equipping other people in your organization to be able to do this trade, this practice. And there, what is your philosophy? What's the way of thinking? How do you coach people? You hire a man, you need him to have the technical skills to work in this space, but then you've got to invent methods to say, I bet you I can get it to break if I, put these combinations together. Let's see.
Yeah. So in some ways, the FE execution or the automation team is at the service of the functional validation team. So in many ways, when we bring someone in, we're trying to give them an understanding that our job is to really find the most bugs at the fastest pace. And if we can deliver a healthy environment to our functional validation team, it gives them a chance to actually focus their energies on writing tests that actually find the most bugs. And if our automation environment is too slow, if the packaging or the dot patching or whatever we're doing to allow them to move quickly with deploying a new test or a new infrastructure, the slower we are at getting that deployment in their hands, the slower the whole system runs. Because we're just one side of it. I kind of joke, we can be the best automation to produce the fastest failures in the industry. However, the faster we produce those failures, the more you create debug and triage and other activities. So if you have a lot of bugs coming in to your products or your ingredients, the entire debug throughput will be slowed down because it's just an overwhelming amount of issues to work at the same time. And the larger number of issues you have at the same time, it's a snowball effect, and it slows the entire velocity of the engine down. So automation is just one vector where we're trying to ensure that the ingredients are getting tested upstream before they collide in the mix of all the other ingredients. And we're trying to build that stable environment for our FE engineers to focus their energies on bug hunting. And if in the end we end up helping them to find the bugs a milestone earlier or 2 milestones earlier, we've been successful in our job. So when we train new engineers, we're trying to give them the big picture of that, train them on all the tools, because there are a lot of tools. It is really a mountain of learning to figure out where is a functional validation engineer going to work. They have to learn, different operating systems. They have to learn different, coding languages, how we're doing our flows, the debug tools, BIOS patches. So we specialize people in certain areas. It really digs them deep into becoming a specialist in one area because the breadth of number of issues is too large. And the history that I have, I've gone through the pains of working through many of those different disciplines, from a single interface to multiple interfaces to platform configurations and automation. So I've seen kind of the end-to-end picture. But the funny thing is that I'm just a functional validation engineer at the end of the day. We have a whole separate group that does electrical, another one that does power and performance, another one that's doing, marginality validation, or even associated with, trying to find defects in the manufacturing process. So we're all working together on the exact same project with different validation disciplines. And my discipline is to try to just ensure that we reduce the number of logic bugs, but I have to partner with these other groups to make sure that they're also working with the same ingredients, same milestones, and same expectations of quality and velocity. So it requires, a big picture look, which is why I enjoyed shifting from the pre-silicon microarchitecture and the low-level interface to more, big picture ideas, because now you get to play with a lot of different toys. And you get to see how these toys interact and really benefit at the end of the day. Because when you productize something, you really, you accomplish something big. Because this is not something that can easily be done by a small army. This is armies of hundreds of people that have to work together toward delivering that product.
Well, the lessons that I take away here and extend to anyone working in any other domain, this is probably one of the most complex build from a hardware, and then code, firmware, and BIOSes, put it all together, and then multiple layers of testing just to get it out to the customer. And so there's probably few other listeners out there that have as complex of an environment. So if they're thinking, man, I've got this hard dependency, how do I rope this dependency that's just hard to into my automated test suite? It can be done. You just have to figure it out. You have to get the right test harnesses, set up your jig, your test lab in the appropriate way, get that thing under test, write the test cases to do it, and then run them over and over again. And for people who are still thinking, well, I hear continuous delivery, and people who deploy and get new release candidates of packages out, every week, every day, but it just can't happen in my place. Firmware, you guys do firmware, your firmware people are kicking out new firmware weekly. And of course, your test people are slinging all kinds of test code, and you can run those, many times a week and different. So if it can happen in your complex environment, it can happen anywhere.
And we have to be extremely flexible, because if an ingredient it drops and it doesn't work, the impact may be detrimental to all teams, whereas other ingredient drops may be isolated to only one domain. So in some cases, we actually use the philosophy that you eat your own dog food. I don't want to monitor a domain, and when their test fails, I don't want to spend time working on a debug failure of a domain that they can fix themselves. So if they're putting bad ingredients in and it doesn't impact everybody else, you need to solve your own problem. But if it's a firmware that's so low level and they turned on a feature for the first time and it breaks my stations and automation, we have to handle that with a little more kid gloves and build more formalities into that delivery process, because it can just cause catastrophic problems. So that's the balance that we trade off. And it kind of breaks some software principles as a software engineer. I should never release code that's going to break. But in practice, we have to move so fast in some areas, like a new test, that I have to be at least aware and allowing some cases of moving faster over perfection. And that's a delicate balance, and it differs for every ingredient. And that's a big part of the hard part of the job too.
That sounds like that's where your feature flags come in. You can turn those features off, knowing
I
that,
wish it was. They don't always have a nice granular cut of feature to feature. They often have some ingredients that overlap each other, so you can't quite easily dissect it.
Yeah, awesome. Well, hey, Kevin, thanks so much for coming on the podcast and talking about how to make sure Xeon processors are operating appropriately before they go into real servers. This has been absolutely fascinating. I appreciate you sharing everything with us.
Yeah, thank you very much, Jeffrey. Enjoyed sharing.
Awesome. And dear listener, until next time, keep shipping.
You've been listening to the Azure DevOps Podcast, a show for developers and DevOps professionals shipping software using Microsoft technologies. Go to www.azuredevops.show for show notes and other episodes. On behalf of your host, Jeffrey Palermo, and our sponsors, thanks for listening, and may God bless you.